Okie dokie geometry folks. So here's a look at chapter 10. Chapter 10 is all about solids now. So we're going from 2 dimensions to 3, which is cool because it's the one we live in. All right, so our first section here is all about these things called prisms. And our goal is to find their surface area and volume. Surface area is not really a big deal because we know all about area from our last chapter. So we'll spend a little bit more time this time, or in this video, talking about volume. Okay, so start off with a quick definition. A prism is just some 3D figure made up of 2 congruent parallel bases. Those bases must be polygons, and their vertices, which are the corresponding vertices, are connected with line segments. I just want to give you this kind of complicated definition so that there's no mistaking what is and what isn't a prism. So here's just some examples and then a non-example, I guess. So some examples, I could draw something like this. So I'll draw this triangle, and I'll draw another triangle over here. So if you imagine this first triangle is in the floor, and then this triangle right here is floating, and it's parallel to the floor. This triangle right here is parallel. And I just need to connect the corresponding vertices with these line segments here. That might have not been the best way to do it. And I'm drawing this one dashed because if this was a solid object, you wouldn't see that last edge there, okay? So when I say corresponding, I just mean that it wouldn't make sense for this corner vertex and this vertex to be connected. That doesn't make any sense. Okay. A non-example of a prism, well, I'll draw one more prism, actually. Would be something like this. I'll draw a pentagon right here, or try to. Something like that. And I'll draw it again up here. The idea here is that they do have to be congruent, so sometimes it's hard to get them to look exactly congruent. But you'll see there. You also might want to just take 20 minutes just practice drawing 3D objects. It's hard, but it actually is pretty fun. Okay. And a non-example of a prism could be, if I start with that triangular one again, I just want to point out this part, connected with single line segments. So I can't have something like this going on. So I'll draw the 2 edges here. But I don't want something like this to happen. That wouldn't be a prism, that'd be some weird thing. So that's a non-example. Okay. When naming these prisms, we name them by their bases. So the 2 congruent sides that are parallel to each other are the bases. So in this case, I'll highlight them. In this pentagon one, the pentagons are the bases. And in this one with the triangles, the triangles are the bases because they're parallel. Okay, we use the bases to name them. And so if the base here is a triangle, this is called a triangular prism. And this one will be a pentagonal prism. Pentagonal prism. Okay. These yellow faces that I highlighted, again, those are the bases. Now, every single flat side, we call it a face. It's just, we give the bases special names to make it easier to point them out. And the other bases, or the other faces, so I'll highlight maybe in blue here. And I'll do this one on the side. Those are just called the lateral faces. Again, just naming them so we can distinguish them. Okay. You notice here, in this prism here on the left, So I'll call this one prism A, the triangular prism. The lateral faces are not all rectangular. One of them might be. The way I drew it, it's a little hard to see, but for sure, I took that the face that the base that's above the floor, and when I slid it over to the right, it takes the side, the face here, and it makes it lean over, and so that side, that face is not a rectangle, it's more a parallelogram. If we look at the pentagonal prism on the right, all of those faces are rectangular. At least I tried to make it when the bases are directly on top of each other. When that happens, we call this one a right prism. So in this case, the pentagonal prism B would be a right prism, and then prism A would be a non-right prism. Okay. Again, just some vocab here. Essentially, you could think of it as a prism would be a right prism if the two bases are floating directly on top of each other and lined up. You can imagine if I had rotated this top base, it wouldn't, your lateral faces wouldn't be rectangles either. I could try to draw that right here, it'd be a little hard. If I drew this, yeah, there's no way, because you kind of took that pentagonal prism B and then twisted it, so maybe our edges here would be like this. Something like that. Okay, so now going on to a little bit of the geometry is we have surface area. The surface area is literally what it sounds like, so it's the area over the entire surface. We already know how to calculate area, so I'm not going to talk too much about it here. But we have a special name for the lateral area, which is just the total area of its lateral faces. You can think of it as the entire surface area minus the area of the bases. I'm going to emphasize this. This is a right prism. I should have put that there, but right prism. Well, I guess you don't need to do that now I think about it. Okay, so let's take a look at this one right here. Just an example is I have this, I don't know if it's actually a trapezoid because I didn't check the dimensions properly, but this is some kind of quadrilateral prism, and I tried to make it very clear that this is a right prism. I'll tell you right now, it is right. So right quadrilateral prism. Okay, and so if I want the area of the faces, I really just need to take a look at everything except these blue ones, except these trapezoid looking things. Okay, let's reset. So because the two quote-unquote trapezoids are floating directly on top of each other, we should be able to see that all of the lateral faces are rectangles, right? And again, because it's a right prism, we know that they are. And so each one is just going to be a rectangle, and we just need to add them up. So I'll call it the lateral area is equal to, let's see, the first rectangle that's closest to us, excuse me, is the area of 8 times 10. The one on, and I'll go clockwise. Then the other one, the next one is 8 times 3. The one in the back is 8 times 5. And then the one on the right side is going to be another 8 times 5. Nothing special here, but I do want to point this out, is that notice that each of these has this height of the prism, and we call the height just the distance between the bases. So I pull it out here, there's 8, and then I have 10, 3, 5, and 5, leaving us with 8 times, let's see, what is that, 23, which is going to simplify down to, what is that, 160 plus 24, 184 square units, whatever those units happen to be. Okay. There's nothing special about this prism other than the fact that it was right. Okay, so notice here that each of these rectangles has the same height, and so you can always pull that height out right here, leaving us with this little shortcut formula that the lateral area of a right prism. This is really important that it's a right prism. If it's not, then the fact that it's been leaned over or twisted actually makes it kind of weird. Right prism is simply equal to the height of the prism times, well, what is this right here? We notice here, we just, all that is 10 plus 5 plus 5 plus 3. That's simply the perimeter of the base. And so I'll label that perimeter of the base. Okay. Just remember that the height here, I should maybe emphasize that, forgot to do that up here. The height of a prism is the perpendicular distance between the bases. And so even if the bases were not directly lined up, such as this case, the actual height that you would want to use would be right here, to wherever this floor is and it's parallel. That would be your height. It would not be this blue height right here. Okay. All right, well, let's actually get onto volume now. So volume, just like how area is the amount of space on your paper it takes up, a drawing takes up, the volume is how much 3D space it takes up. So think of it as a solid object in your room or on your desk. Okay. Just like how we could measure area with unit squares, we'll use these unit cubes to measure volume. Okay. So let's start off with this one right here. So I got a right rectangular prism. Okay, so what's nice about this one is that, well, the fact that it's a rectangular, so we can fit the cubes in it easily. And I'm going to draw the cubes out just so we can see what's going on. So I can split it up as to 4. So that's 4 across there. There's 2 rows down here. Oops. Right down the middle. 4. And then 3 left. So let's see, that's 1, 2, 3. And so we can count the unit cubes. We can chop the prism into layers and see in this layer right here, the top one, how many unit cubes are there. We can count them at this point, but since we see that there's 4 rows of 2, that'd be 8 unit tiles, or sorry, unit cubes in that one layer. Oops, let's do this. 4 times 2 equals 8 unit cubes. And then we use the last dimension, the height of 3, to figure out how many layers there actually are. So 3 layers of 8 cubes equals 3 times 8, which is 24 units cubed. And that would be our volume. Okay. So we can use this idea, and then we'll do one more with this triangular prism, and before we get to our little formula here, is if I think about this triangular prism, well, I like to chop it up into layers between the bases. So notice here in the rectangular prism example, it didn't matter if I had used 3 layers or 2 layers or 4 layers, it wouldn't have mattered, right? Because it's a rectangle. In this case, with the triangles, I do want to make sure I'm chopping up the layers this way with a height of 8. Oopsies. Okay, so let's see. Chop in half, therefore. Let's see, chop in half again, and then again. Okay. So we know that each of these is 1 layer, and there's 8 of them. Now, because the bases are floating directly on top of each other, I think it makes sense that each of the layers is going to be exactly the same, right? So I'm going to take a look at just one here. So what I'm doing here is taking a bird's eye view of this prism. So this is a top-down view. Okay. If we just look at this as an area problem again, we know that the area of this guy is equal to 3 times 5 divided by 2, which is 7.5 square units. Okay. So all we're doing is that when we now translate that into a 3-dimensional problem, is that each of these layers, remember, has a height of 1 unit. 1, 2, 3, 4, 5, 6, 7, 8. And we know that how many now square units are going to fit into this little triangle is the 7.5. And so I have 8 layers, I'll say, of 7.5, not square units now, but they'd be cubes, because I've now translated them to 3D, which turns into 8 layers, or 8 times 7.5, which is 60 cubic units, or I'll say units cubed now. Alrighty. So notice here, in both cases, what did we really do? Is all we did was found the area of one of the bases. That's this in green. And we multiplied that by the height. And so the volume of a right prism is equal to the area of the base. Again, either base, because the bases should be congruent, times the height. That's our first little introduction into solids and their volumes. Okie dokie.